Okay, so we got a lot of people in office hours today, and we've got a lot of questions we are going to work on. We're just going to get to it. Anyone who comes in, if you've got a question, feel free to chime in. And if you come in, or if you think of another question you want to work on, just go ahead and put it in the chat, and we'll get to it. So we are looking first at Mastery Question 11, number 1. So we're looking right here at this one. In this question, we might have different numbers. Actually, I'm looking at your numbers. No, it was Caitlin. I'm looking at your numbers. So it says, what volume of 0.1616 molar potassium hydroxide is required to react with all of the lead 2 plus ions in 96.2 milliliters of 0.108? That's a lot of numbers. Start by writing the balanced chemical equation. Okay, so we're going to do KOH plus Pb2 plus goes to, we're just going to do a little flip-flop. The lead's going to replace the potassium. Hydroxide is going to move over. That's going to be PbOH plus K plus. And the first thing we should realize is that if we want to have this charge balanced, right, first thing we have to do is make a good compound. This is going to be PbOH2. And then I'm going to go ahead and balance the chemical equation after I've got my good compounds with the good subscripts. So I'll put a 2 there and a 2 there. 2 potassiums, 2 potassiums, 2 hydroxides, 2 hydroxides, 1 lead, 1 lead. Now I want to find the equal moles. So I'm going to find the moles of lead 2 plus we have. So I'm going to take the 0.01802 moles of Pb per 1 liter. I'm going to multiply by the volume so we can get to moles, and that's going to be 96.2 milliliters times 1 liter. Yeah, 1 liter on top. 1,000 milliliters. That'll cancel out milliliters, that'll cancel out liters. This will get us our moles of lead 2 plus. Calculator. And I get something like 0.001733. If you've got a calculator handy, please calculate with me because I am notorious for making mistakes on my calculator, especially when I'm going fast because I want to get through all the problems. And this is going to be the moles of lead 2 plus. And the mistake that I think you were making, or that the person who was helping you was making, was forgetting about the mole ratio properly. Converting from moles of lead to moles of hydroxide needed, you would need to use essentially the recipe that's going to tell us the ratio of lead to hydroxide. And I'm going to have 2 moles of OH minus for every 1 mole Pb2 plus. And I think that's going to double the number that you have and get you the right answer. So this will be times 2. Did I miss something? Oh my goodness. I don't know where I got this number from. I just looked at the wrong thing. So if you were following along, Caitlin.
Yeah, I was really confused.
This is totally right if these were our numbers, but your number is actually, your number is 100 times bigger than what I put, right? It's 1.8. 1.08. Just a little dyslexia on my part. 1.08. I flipped the 0 and the 1 when I was doing the problem. So that's going to change our number slightly. 1.0802 times 0.0962. And that gets us 0.1039 times 2. Now this is more what I was expecting. And that's going to give us 0.2078 moles of OH minus. Notice I'm really careful in my labeling of which thing I'm talking about the moles of, since there's 4 different things in this reaction, 4 different things we could talk about in terms of moles. And then I want to get to a volume, and we know that molarity times volume equals moles. And from the problem already, we are given the molarity of hydroxide, we have the moles of hydroxide, we should be able to calculate the volume. We're going to take that moles, we're going to divide by the molarity, 0.1616. And if you do that, and this is for Caitlin's particular numbers, you get volume is equal to 0.2078 divided by your molarity, which is 0.1616 moles per liter, moles, and that should get you the answer. So again, I think you did most of it. I think you just forgot that factor of 2. Does that seem correct? Does that seem like what went wrong?
Yeah, but I put that number in, and it still says it's incorrect.
Did you remember to convert to milliliters?
Oh, that's why I was wrong.
Yeah, so if you put in 1.28 liters, it's asking for the answer in milliliters.
Okay, thank you.
So, and what's nice about this as a starting problem for what we're working on today is this process for stoichiometry is the same stuff we're doing in all of the problems, right? We start out with some measured amount of material, we convert to a number of moles, we use the mole ratio to convert to the other thing we're interested in our reaction, and then we convert back to some measurable thing. We always are pretty much doing those 4 steps. Step 0 is making our balanced chemical equation. And you'll notice as we go through almost all of these, we're either going to be doing this process for stoichiometry, or we're going to be doing some combustion analysis problem, which is similar but slightly different. Any questions about this one before I move on? Okay. Just adding another one to the list before I forget. Okay. Okay. Let's see. Report 2. Oh yeah, this one is interesting. So this one is going to be quite dependent on what you've got set up so far. And I just want to double check who's asking this one. Paradi, this is your question, right?
Yeah.
How do you say that?
Parody?
Parody. Okay.
Yeah.
Parody. Let's see.
I think Liv and Kylie have another question before you completely.
Oh. How did you get moles of lead? Yeah, it's in the problem. Liv, that was given in the problem.
Okay, thank you.
Yeah. So let's see here. So at this point, you've got an unknown. You've got the molar mass of your unknown from the information above. Is it just getting your molecular formula?
Yeah.
Okay. Did you make sure? So this problem is pretty interesting. So from the experiment, you should get some molecular weight, some molar mass for your unknown acid. What molar mass did you get for your unknown acid?
I got 176.14 grams over moles.
Now, the other part is you need the empirical formulas for acid A and acid B. Did you know what that was talking about?
Yeah, that was from the prep 1, right? That's what we.
Yeah.
Yeah.
So from prep 1, we've got 2 different possibilities. We've got acid A and we've got acid B. Did you get the empirical masses of those 2?
Yeah, I got for A, I got 88.04, and for B, I got 152.08.
Okay. Okay, so what did you put for your answer?
Well, that's where I got stuck. Like, I didn't know where to go with that.
After you got here. Okay, so here's the important thing to remember. When we're looking at an empirical formula, I'm going to make up something different than what we have in our acid A, acid B. I'm going to make an empirical formula that's like C2H4O. Right? If this is our empirical, it can be C2H4O, or it could be C4H8O2, or it could be C6H12O3, or it could be C8H16O4, right? Even though we've got these different molecular formulas, they all, when you get the smallest ratio between them, you're going to get the same empirical formula for all of them.
Yeah.
So that means when we look at what you have going on, we look at 176 and we say, okay, is that close to 152?
Somewhat, yeah.
Kinda. What about double 88?
It's a bit closer.
It's a bit closer. So my guess is if I take 88 times 2, I get exactly 176.
Oh, okay.
So you probably have double this empirical formula to get your molecular formula, right? So your answer could have been this one, double this, triple this, quadruple this, or double this, triple this, quadruple this, right? It could have been any of those since these were empiricals. It's anything that has the same least ratio.
Got it. Okay. Thank you.
You bet. Any other questions on that one? Okay, let's hop over to mastery question 11, number 3. Okay. Now this one, I was confused. No one's asked me about this one yet, which was kind of strange to me, but that's okay. Concentrated hydrochloric acid is a solution that is 37.5 mass per unit volume. So we can think of that as 375 grams per 100 milliliters, something like that, right? Or 350 grams per liter? I gotta think about that for a moment. But all of that's kind of like extra information as far as I can tell. We've got an old bottle of HCl with an unknown concentration. What's the concentration in the bottle of 9.65 milliliters of 9 molar sodium hydroxide is required to reach the equivalence point with 25 milliliters of the acid, right? So this is really similar to what we did in mastery question 1, number 1, where we're going to be getting this kind of equal molar point. And this is nice because it's a 1-to-1 ratio, so it's a little bit easier. So we're going to start by just writing down all of the explicit information in the problem, all of the stuff that they give us outright. 9.65 milliliters at 9 molar NaOH. And they tell us 25 milliliters acid. And we want to find percent weight by volume. Now, percent weight by volume is really just kind of another way we could do concentration. And you can imagine how weight by volume is nicer for people who don't do chemistry. Because you got a solution, you put 5 grams of your stuff in, and you've got 5% by volume, right? It's a lot easier to think about. There's other units as well that are practical in like industrial settings when you're looking at molality and things like that. But for us in this class, we do almost all molarity. And this is really going to be about finding the concentration. So we can think about this in the exact same way we did before. Since we are told we're at the equivalence point, we can start by finding the moles of sodium hydroxide, use a mole ratio to relate that to the moles of hydrochloric acid, and then convert that back to a mass of hydrochloric acid that's in there after we have the moles of hydrochloric acid. And we can figure out how much of that is grams per milliliter. So let's go ahead and do that. Right, and I strongly encourage all of you to kind of do that thought process. I think you can all agree the hardest part of chemistry problems is figuring out what the heck you're supposed to do, right? Addition, subtraction, division, multiplication, all that stuff's easy, but it's setting up the equations that are kind of the tricky part. So in this one, we're going to go ahead, we're going to calculate the moles of sodium hydroxide, 9.65 divided by 1,000. Yep, okay. Times 9.0 moles per liter. The liters will cancel out, the milliliters will cancel out, and this will give us moles of sodium hydroxide. I'm feeling pretty eager, so I'm going to go ahead and put in our conversion step as well, which is going to be 1 mole of HCl. I should put specifically OH minus there. 1 mole of HCl for every 1 mole NaOH. That 1-to-1 ratio is really important. And that will get us our moles of HCl. Calculator. 0.00965 times 9. So this gives us, assuming I did my calculation correctly, hopefully you're following along and you'll correct me if I'm wrong, 0.08685 moles HCl. Now, we're not done yet, but we've kind of got the essentials, right? We've got moles and we've got volume. Our moles we just calculated by using our equivalence point definition. So we know that the moles of acid are equal to the moles of base with our mole ratio taken into account. And we're just given the volume. But what we're asked for is mass per unit volume. So I've got to take this moles of HCl, right? If we just wanted molarity, we'd be done. Divide those two numbers and you're good. If we want mass per unit volume, we're going to have to take that moles and multiply by molecular weight. And that should convert us to mass. So we need the molecular weight of HCl, which is going to be 36.45. And that's going to give us 3.165 divided by 25. Which is equal to, I don't know why I put an error there, 0.1266. For the numbers I had in my problem, this is what I get. And I think that the part that's confusing me is why they gave you that 37.5 that we didn't need. Maybe just to show how the concentration of hydrochloric acid can change over time. But about 12% by mass. Mass to weight to volume ratio. So that was mastery question 11, number 3. It uses some different units, but it's not much trickier than the things we've been doing. Number 4, however, this one, okay, I'll be honest with all of you. I probably shouldn't, well, here, hold on. I'm going to pause. So this problem is pretty tricky. Mastery question 11, number 4. I'm going to go ahead and read it out, and it has to do, it's really the essentially the same concepts that we've been working with, but it adds an extra kind of layer to it. 0.522 gram of carbonate salts is added to a flask. The only thing you know is that the per formula unit, there's only one carbonate anion. But the identity of the cation, or cations, is unknown. To determine the identity, we do a titration, kind of like we did in the lab video. But you go too far. You essentially mess up and you put in too much acid, and you go, oh no, now we have to figure out how much extra acid we put in. So the remaining solution is titrated with sodium hydroxide to get rid of the extra acid. This is also referred to as a back titration. And essentially, if you remember from the titration video I did, there was this point where I went too far and made it too dark pink. And you could theoretically then get a different solution in and get rid of the dark pink and measure how much it takes to get rid of the dark pink. So you can figure out how much you messed up by. So essentially with this problem, so we're going to go ahead, we're going to write down all of the information we have given, all of our explicit information, and we'll work from there. 0.522 grams sample. We're going to do 15 milliliters of 1 molar sulfuric acid. Noticing that there are 2 protons for that sulfuric acid is going to be important. And then we're also going to add 33.915 milliliters at 0.577 molar NaOH. And essentially what we're dealing with here is the moles of acid have to be equal to the moles of base. Same thing we've seen, right? We want to start with our conceptual kind of work. So our moles of acid and our moles of base need to be equal to each other. I keep opening the wrong thing. There we go. Okay. So I'm going to go ahead and write that. This is a sample of carbonate. And we're actually going to be doing 2 separate chemical reactions in this. We're going to do sulfuric acid with carbonate and sulfuric acid with sodium hydroxide. So if we stop at the correct equivalence point eventually, my moles of H2SO4 has to be equal to the moles of carbonate plus the moles NaOH and for both of these, since we're doing 2 separate reactions, we're going to need 2 separate mole ratios for this. But that problem we just did, right? We can do a problem that's just find the equal moles. This problem we just did, just find the equal moles, and now we just got to put those 2 ideas together. So this is kind of conceptually how we can look at it. I'm of course, going to start by writing down my reaction of carbonate with sulfuric acid and then my reaction of sodium hydroxide with sulfuric acid so I can get these mole ratios. But when we start looking at this, oh, we'll get to that in a moment. Let's start with the chemical reactions. So I'm going to have H2SO4 plus, I'm just going to call it unknown. What's a good unknown? Let's call it X. We've got unknown X, CO3, and that's going to go to XSO4 plus CO2 plus H2O. And we're going to get, and that should be balanced already. 2 hydrogens, 2 hydrogens, 2, 3 oxygens, 3 oxygens, 1 sulfate, 1 sulfate, 1 X, 1 X. 1 carbon, 1 carbon. You could argue with me and say, well, what if there are 2 X's? Well, then it would be X2, X2, and you'll notice my balancing coefficients won't change. So whether it's X1 or X2, whether this is a +1 cation or a +2 cation, is actually not going to change the stoichiometry, since it's really the X is kind of a spectator ion, actually. So we'll just leave it as X1 for now, but we'll have to think about that later. Second reaction is also going to be sulfuric acid, H2SO4, reacting with sodium hydroxide. And that is going to go to sodium sulfate, Na2SO4, plus H2O. And I got a little lazy. Let's not get lazy. We got to keep states of matter on all of this. I'm going to assume that this is going to be something aqueous. It would be mean if it were not. But we should always have states of matter on to make sure our chemical equation is correct. I also jumped the charge balancing. I knew it was going to be 2 sulfates at -2, so I needed 2 sodiums there. And this means we've got to do some balancing. I'm going to need my 2 sodiums. And then I've got 2 waters that are going to be produced. So I've got 2 OHs to go with the 2 H's there. That'll give me 2 H2Os. At that point, we can kind of erase this stuff in blue now that we've thought about it a little bit. And we can plug in what our mole ratio for carbonate is. That's going to be a 1-to-1 ratio. And then our mole ratio for hydroxide. Ooh, and we've got to be careful. I want moles of sodium hydroxide to be converted to sulfuric acid. So I'm going to want this to be 1 mole H2SO4. Oh, subscript 4, not superscript. For every 1 mole, for every 2 moles NaOH. So being really careful, you notice for the carbonate, I didn't have to think too hard because it's 1-to-1. So don't need to think, it's 1. For this one, a factor of 2 versus a factor of 1/2 can make a big difference. So we have to make sure that we're careful with that. And it is 2 moles of sodium hydroxide for every mole of sulfuric acid. No, Laura, there's usually not this number of students in office hours. And as you come up, anyone who's come in and is watching this, as you come up with questions, if you post them in the chat, I'll add it to the list, but you can see what we're working on right now. Let me give that a little circle. We're working on that one right now. Mastery question 11, number 4. Forgot to label that at the beginning. So, I'm going to erase this part. I'll leave the part in blue. We don't need to erase that. So now I'm going to, now that I've thought about my chemical system, it's given me this information about how these reactants are going to relate to each other. And now I can go ahead and think, well, what pieces do I need to get the moles of carbonate? So I'm going to need the molarity of H2SO4 times the volume of H2SO4 equal to the grams of carbonate, unknown carbonate, times the molecular weight of unknown carbonate, plus, times 1. Now, I know multiplying by 1 is not mathematically interesting, but that's really important for getting our units correct. Plus the molarity, NaOH, times the volume of NaOH. And when we think about it this way, saying that my moles of acid have to be equal to the moles of things it's reacting with, taking the mole ratios into account, we can go through and we can say, okay, molarity of sulfuric acid, I've got that. Volume of sulfuric acid, I've got that. Grams of sample, I've got that. Molecular weight of carbonate, I don't got that. That's what we're trying to find. 1-to-1 ratio, and y'all need to yell at me when I do this. 1-to-2 ratio. Don't forget the 1-to-2 ratio or it's going to get ruined. Molarity of NaOH, we've got that. Volume of NaOH, we've got that. So in this equation, there's only one thing we don't know. The molecular weight of the carbonate, of the unknown carbonate. So at this point, we just plug numbers in and solve. Go ahead and try that out real quick. I'm going to be a little slow with my calculator, but you can punch numbers in. And we'll see if we get something reasonable. I'm first going to write down everything plugged in. You'll notice I converted to liters in my head real quick on this. So I'm going to have 0.01. Let's do this. 0.577, 0.033915 divided by 2. Plus 0.015. Oh, I made another mistake. And I figured it out right as I went to solve this. What are the units of molecular weight? You can type it in the chat if you're feeling brave. Molecular weight is grams per... grams per mole. So if I multiply here, I'm going to get grams times grams. I need this to be a divide by. And as soon as I went to get my final answer, I got something that was like my molecular weight was like 0.000 something. And I was like, that doesn't seem right. Okay. So again, let's make sure we've got that divide by in there. Grams divided by molecular weight to get moles. And let's see. Now I got to redo that. Oh, 0.577 times 0.033915 divided by 2. Negative plus 0.015. Okay. Then we're going to inverse times 0.522. And I get a particular value. The value I get for this is I get my molecular weight is equal to 100.08 grams per mole. And once we get that value of 100.08 grams per mole, we say, okay, well, what carbonates could that possibly be? What unknown carbonates? And, you know, it's kind of hard to tell right off the bat. So what we're going to do is go back to this idea of the XCO3. And we know the mass of carbon and oxygen, so we can subtract that out and just get the mass of X. So my mass X, after I subtract off the carbonate mass of 60, my mass X is going to be 40 grams per mole. And I'm going to put X in quotes. I don't know if that's 1X or 2X, but I'm going to look at the periodic table. And it looks like calcium. Calcium carbonate would be exactly 100.08 grams per mole. So that looks like it's calcium. Now, we do want to consider, what if it was X sub 2? That would be half this value, because I'd have 2 X's. So I'd look for things that are also 20 grams per mole. And that would be neon, is 20 grams per mole. Neon or fluorine, and that doesn't make any sense because neither of those are cations. So I'm relatively confident that the problem I got was calcium carbonate. Now, again, you'll notice the hard work here was just this conceptual thinking of how we put these pieces together. Questions? Okay.
Yeah, I have a question.
Oh, sure. What's up?
How did you go about solving that equation for the question mark? I got really lost in there.
Oh, for this. Okay. So first off, I had a typo. You can make sure that you had grams divided by molecular weight, not times. Otherwise that's going to ruin everything. And then I had I did my molarity times my volume. So that's going to give me 0.015 because it's just a 1. And then over here, I'm going to take 0.57 times 0.03915 divided by 2. I'm going to subtract that over. So I've got number equals 0.522 divided by question mark. I'm then going to multiply by question mark and divide that over. So I get the question mark alone. And I'm going to have 0.522 divided by the number of moles that I have after I do the subtraction. Was that?
Yeah, perfect.
Okay. Other questions before we move on? Okay. So that was master question 11, 3, and 4 done. We're going to go ahead and look at mastery question 12, number 3. And we're going to particularly look at part 2. So if you're like, whoa, but I need help with part 1, check out office hours yesterday or come back at the end of office hours and we'll work on it. But I did a pretty thorough explanation for that problem yesterday. And of course, during office hours, I'm always happy to go over it again. I just want to kind of try to get new things done first. Question 12. So this is the... Oh, I'm looking at mastery question 11. That's why it's not making sense. So question 3 continued. Is that the one that you wanted to look at? Scroll back and see who asked this one. Ashley was, yeah, so Ashley says, yes, that part. Okay. Ashley, I don't know which thing you had. So I'm going to do it for the thing I had. Oh. Let's see. So for my example, let's say we did the first part right. I ended up with MnS3. Manganese 6 sulfide. And we want to know the mass percent of manganese in this. And the mistake that a lot of people make, they instantly start trying to pull information from the problem. They try to use that mass that was given. It turns out that mass that was given was not useful in the problem. So what we want to do is we can think about this just in terms of the mass ratio. So I can look at this MnS3, and I can get the molecular weight of this thing and then figure out how much of it is just manganese. Since I've got one manganese, I can put 54.94 times 1 on top. That's my one manganese. Divided by 54.94 times 1 plus 32.07 times 3. Right? And this calculation should give me the mass of manganese divided by the total mass of the compound, which will give me some fraction. So for my example that I happen to have, manganese S3, 54.94 plus 32.07 times 3 inverted times 54.94. I'm going to get this is equal to 0.3648 or 36.48%. And again, it's one of those things that is deceptively simple. It's that problem of recognizing that we don't need to try and involve all of the data from previous parts. We can really just think, this is my compound. What percentage of this compound by mass is manganese? So I'm going to do the mass of manganese divided by the mass of the compound. Okay. Okay. So I just realized who that is. Okay, so questions on this problem? Did that clear things up for you? I think this was Ashley asking about this one. Yeah, it was okay. Okay. Yeah, there's a lot of ways where you can make this extra complicated that you don't really need to get into that headache. Okay. This is, now, unfortunately, this is one of the problems that has an array issue. So if you hit change problem values, it should reset the array and fix that for you. Mastery question 12, number 4 and number 5. On to mastery question 12. So continuing on that, mastery question 12, 4 and 5. I'm frustrated with question 5 right now, and I apologize for that. Question 4 and question 5 are really similar to each other. And they're going to follow the same kind of things we saw in Mastery Question 1 and in Mastery Question 11, Mastery Question 11, Problem 1 and Problem 3, where we've got some equivalence point. Our moles of acid are going to be equal to our moles of base. So stop me if you've heard this one before. We've got sodium hydroxide to reach the equivalence point of the compound below, where we've got a particular number of grams. Let's write down our actual parts that were given. 0.9169 grams of acid. We are also at 0.3366 molarity sodium hydroxide. And what we want to find, the thing we want to find, is volume of sodium hydroxide. So when we look at this, it specifically says there's a couple important things in the problem. It specifically says equivalence point is reached. So that means my moles of acid equals my moles of base, with whatever mole ratio is necessary in the chemical reaction. So there's that part. That's important. That's a phrase that, gives us important information. We can also use the molecular structure that we're given. And the reason that's going to be important is because there's always some inferred or some implied information in the problem, right? And somehow, moles of acid is going to be, when we think about the information we're given, volume times molarity would give us the moles of base. Mass divided by molecular weight would give us the moles of acid. So the important part here is first that we can recognize that those are the two equations we're going to be using. And then we also have to be able to recognize how we can get the mass of this compound just from the line drawing. So that's 1, 2, 3, 4 carbons. 3, 6, 7, 8 hydrogens. 2 oxygens. That's going to have a molecular weight associated with it. Okay, calculator's out. Make sure you're calculating this. 12 times 4 plus 8 plus 32. Always have your periodic table handy. 4 carbons, 8 hydrogens, 3, 6, 7, 8. Okay. I think this is the problem. One of the problems I messed up my simple math with yesterday, and I kept getting a number different than 88. But once we have this extra piece of information and this extra piece of information, this really looks like a lot of the problems we've been doing. My moles of acid is going to be my mass times 1 over my molecular weight. That's going to be equal to my moles of base, which is going to be molarity times volume. And for my mole ratio, from the structure, I can see that this is a carboxylic acid. I'm going to have 1 acidic hydrogen to go with the hydroxide, 1-to-1 mole ratio. And we can go through, after we've got this kind of conceptual thinking, we've got mass, we've got molecular weight, we've got molarity. We can now solve for volume. 0.916 divided by 88 divided by 0.3366. You get volume is equal to 0.0309 liters. Making sure convert to milliliters because it asks for the answer in milliliters. Questions on that one? Let's see, I'm scrolling back to figure out who asked this. Semester question 12, number 4. Did that make sense to you, Yvette?
Yeah, so you just multiplied the grams, and you divided the grams by the molecular weight.
Yeah, and it makes sense when we look at the units for that, right? So our mass is going to be 0.916 grams of acid, and then I'm going to multiply by 1 mole of acid is 88 grams, right? Dividing by the molecular weight, you can also think of that as multiplying by the reciprocal. And I like multiplying by the reciprocal because you can really easily see that the grams of acid cancels out and you're left with moles of acid. And question 5 is essentially the same thing, except for instead of having a 1-to-1 ratio, you've got a different ratio there. And I'm just going to double check something real quick. As my computer loads. Yep, you're just going to have something besides a 1-to-1 ratio because you're going to have multiple carboxylic acid groups on that compound. I'm going to let you work on that one. If you want me to come back to that, let me know. But give it a shot and see if you can get it just from the framework of this problem that we did together. Okay. Losing track of the world. Prep 2. Let's take a look at Prep 2. I think Prep 2 is really similar to this as well. Prep 2, a little bit different. Okay. So Prep 2, this is actually a prep I wrote like a year ago. And it's supposed to get us to think really practically about what we're doing. So, and we can kind of do this, a lot of this problem with just looking at conceptual ideas without actually touching a calculator. Ruby's still here, right? Yeah, Ruby, hey. So, if we can do part 1b right, I like to, so for me, sometimes thinking about this in terms of chemical compounds gets too abstract. So I like thinking about it in terms of sweet tea. So I'm going to think about this entire thing. I like thinking about concentration in terms of sweet tea. So when you take out the 5 ml portion, you're taking a sip of sweet tea. It doesn't matter if we have this big jug of sweet tea and we fill like 6 cups with sweet tea, they all taste the same amount of sweet. But if I poured just a little bit, if I poured like a little sweet tea and then a bunch of water on top of it, it tastes less sweet, right? I haven't reduced the amount of sugar that's in the cup, but I've diluted it so each sip you take, you're getting less sugar per sip. And this is the idea that if you had a cup and you start with some amount of sugar in it, you add a little water, each sip you get, so that amount of sugar is not going to change. That's your number of moles of sugar in there. And then as you add water, you're just going to dilute it more and more, and it's going to taste less and less sweet the more water you add. So we're looking at part B and bringing that forward. We've got 5 ml portion of part A. So essentially the moles should be the same, right? The moles from part B should be the same as part C. We don't change the moles when we add water. We've got the same amount of stuff there. We've just increased the water. But we do change the concentration because now each sip is a little less sweet, or each sip you get less with each volume of solution. So with that conceptual thinking, let's go ahead and do this. And we've got to do it all the way, since this all depends on each other. We've got to do this straight through. We've got to do all the parts together. And if my folksy sweet tea example did not help, just forget it. Okay, so we start with a grams of sodium, molarity of sodium hydroxide in a specific volume. We've got 43.79 milliliters times 1 liter has 1,000 milliliters times 0.172 moles per liter. Right, so that's going to be our concentration of sodium hydroxide. This will give us how many moles are in a container, and we're going to kind of have this visual thing to go along with it, right? I've got this container. It's got a specific number of moles in it, and we're going to go ahead and calculate that specific number of moles now. 43.79 divided by 1,000. Times 0.172, and again, these are my numbers, yours might be slightly different. And that's going to give us 0.00755, whoa, 516 moles NaOH. Now, in step B, what we do is we transfer a 5 milliliter portion. So we just take out a little bit, right? And you can imagine, I've got 43 parts, so you can imagine if I cut this into 9 parts. 1, 2, 3, 4, 5, 6, 7, 8, 9. Each of those 9 parts is about 5 mils. But because the solution is kind of uniform, we're assuming a uniform solution, each of those 9 parts is going to have the same number of moles per liter. So when we take out just one of these portions and move it, we shouldn't change the concentration, but I'm not taking all of the solution. So if we took 9 sips of our sweet tea, it all tastes the same sweet, but we're going to take out 1 serving, and we're going to add water to it. So when I take this portion out, it's got the same concentration if I don't add any water to it, but since it's a smaller portion of the whole, it's going to have a lower number of moles because I didn't take all the moles. So in order to get the number of moles, I'm going to multiply by 0.005 liters. It specifically said 5 milliliters removed. So I multiply those two together, and you will not be surprised. 0.172 times 0.005. That's going to get me 0.00086, which is about 1/9 of our original. That fractional I'm thinking doesn't really matter, but this is going to be our moles in that new sample. So that is our concentration doesn't change when we take a small sample, but our number of moles is not the same. Then we go on to part C, and we say, okay, we're going to take this same thing and to that original amount, I'm going to add a bunch of water. Now that water is going to cause this thing to dilute and kind of move everything around. Now, in adding water, I haven't taken any sodium hydroxide out. I haven't added any sodium hydroxide in. So my moles of sodium hydroxide is actually going to be the same in that case, except I forgot a 0. Right? I haven't just adding water doesn't change the amount of sodium hydroxide that's there. But then I add extra water, so while the number of moles doesn't change, the total volume does. So when I calculate my concentration, it's going to be 0.0086 moles over the total volume, which in this case, the total volume is now going to be 0.005 plus the 20 added. Uh, 25 milliliters. I like to do it with the plus so you can kind of see the 5 mil portion plus the 20 mils of water added to get us the total concentration. And that's going to be how we get our new concentration. And then part D is essentially a weird way of asking a titration question, which is thinking back on this original sample, how would you get an equal number of moles to hydrochloric acid? And this is all supposed to be kind of the experimental thinking of doing a titration, which when you're doing a lot of mathematical processing and doing a bunch of problems on paper, you don't always think about the kind of experimental practicality of it. Let's go ahead and get this number 0.0086 divided by, oh, forgot. Why do I keep forgetting that 0? .00086 divided by 0.025. 0.034 molarity. And not surprising, I took a 5 ml portion and diluted it, and I end up getting a lower concentration because I've reduced the number of moles. Is this helping, Yvette? Wait, did you just? Oh. Ruby, sorry. That was the last question. My apologies.
Okay.
Is this making sense?
Yes.
Great.
Thank you.
Okay. And then part D is very similar to the other questions we've done, mastery question 11, mastery question 11.3, 11.1, and 12.4 are all going to be really similar to D, where you've got number of moles of acid equal to number of moles of base, and you've got to solve for the missing volume. Do you want to see me do that one?
It's okay. I think I can figure it out.
Okay. Give it a shot. I'll give it an underline. So if you decide you want us to come back to that one, give me a shout and we'll come back to that one. But go ahead and give it a shot. So yeah, let me pause this real quick. Next in line for solving is the titration questions, number 4. Oh yeah. I did this one yesterday, I think. Who asked this one? So I'm, of course, always happy to do problems again, but I just want to make sure the person who asked didn't run away and already get it. Ruby, you're still here.
Yeah.
You want to see this one?
I did watch the video you posted yesterday,
Uh-huh.
and you only did the first half. You didn't do the part for, oh wait, is this the one where it's like H2O and then carbon for the first one?
Yeah, CO2 and H2O.
For the H2O part, every time I did it, it said that my equation wasn't balanced.
Let's take a look at that. Do you remember what you got for your balanced equation? And I don't know, did you have octane, or is it one of those ones that mixes it up and did something else besides octane?
I'm trying to find it. Just
Okay, go ahead and pull that up. I'll do the problem that I've got in front of me, which is C8H18 plus O2 goes to CO2 plus H2O. Balancing coefficients, 18, 2, 16. And this is where I couldn't do math yesterday, but fortunately, I remember my mistakes, so I don't repeat them too often.
Yeah, I do have octane.
Okay. Did you get these balancing coefficients to 25, 16, 18?
Yes.
Okay. Let's see if we can figure out what's going wrong. So let's do the conceptual thinking first. We've got some... Did you get your mass of carbon dioxide correct?
I guess I didn't, because it just, when I enter it, it says check your balanced chemical equation to get the correct molar ratios.
Okay. I think it gives that same mistake. Yeah, it gives the same help hint whether for both of them, so it's hard to tell which one you got right, which one you got wrong. let's go ahead and try it. So I'm gonna, you watched the video yesterday, so let's go ahead and think about what's going on. Conceptually, we've got excess oxygen, so it's gonna be moles of octane times mole ratio, which is going to be 18 moles H2O for every 2 moles of octane. That should get us our moles of H2O. And then if I multiply by 18 grams of H2O for every 1 mole H2O, that should get us back to moles. So that should get us back to grams. So we go moles of octane to moles of water to grams of water. And the only thing that we're missing is how we get from the silly units they gave us of 1.37 gallons, and it's not really the fault of the problem, it's the fault of the United States, but let's not get into it. Gallons, fine. We need to convert gallons to liters to grams, so we're going to go gallons to liters to grams and then to moles. And here, to get gallons to liters, that's just a unit conversion. To get from liters to grams, that's going to be density. And to get from grams to moles, that's going to be molecular weight. And if these types of mapping the problems doesn't help you, that's okay. I'm just showing you how I kind of map out my thinking before I start crunching things. And I want to make sure I know how to do the unit conversion. I want to make sure I've got the density of octane, and I want to make sure I know how to get the molecular weight. Because if I can do that, then this is going to be pretty straightforward. So now that we've done our thinking, we can go ahead and put in the specific numbers. 1.37 gallons. We've got 4 quarts per gallon. And we've got, I need the equation sheet for this one. And we've got I'm going to put it in milliliters because that's what the density is in. 1,000 milliliters for every 1.056 quarts. So that should get us to gallons, to quarts, to milliliters. And then if I multiply by the density, which is going to be 0.703 grams per milliliter, that should get us to grams. And then we can even put in our next mathematical step if we wanted to, but I don't want to do too much all at once because I'm prone to calculator mistakes. So I'm just going to do these steps first and see how it looks. .37 times 4 divided by 1.056 times 1,000 times 0.703, and we end up with 3,648 grams octane. It's a lot of octane, but considering that it's 1.37 gallons, that's a pretty big thing. It's like 3 kilograms, like 2.5 pounds, like 3 kilograms would be what, like, it's heavy, 6 pounds. So there's our grams of octane. Then we can take our molecular weight. Oh, this was the other place I messed up. 12 times 8 plus 18 is 114. 1 mole of octane is 114 grams of octane. That is going to get us this number of moles of octane times 3,648. Oh, I messed up. Times 3,648. Okay, good thing I wrote things down because I just punched it into my calculator wrong. 3,648 divided by 1.4. Oh no, it was just a really round number. I rounded too much. 32 moles. So I can now take this 32 moles, plug it in for my moles of octane, use my mole ratio of water to octane and my molecular weight of water, and that should get me my grams of water. 32 times 9 times 18. And I should have 5,184. So the place where a lot of people mess up on this is the molar coefficients and recognizing that it's 18 to 2, not 2 to 18. That's the common mistakes. Okay, let's see. That was question number 4. Did that help, Ruby? I think Ruby left. I must have helped. Oh no, you turned on your camera. This is just I've gotten so used to just seeing black squares that it throws me off when I can see faces.
Yeah, I think I just messed up with the conversions of changing it to grams. I changed it to something else.
Totally reasonable. Like the funny thing about these problems is, and you'll notice I have colleagues who will do 1, 2, 3, 4, 5, 6, 7. They'll just put all 7 multiplications together in one long string, and they'll do their unit canceling, and they'll be like, great. I have a tendency to always mess up my calculations when I do that. So I almost always break them into like steps of 3 and write down my result for each step of 3. Because otherwise I just mess it up. It's just something I know about myself. Small steps.
Thank you.
You bet. Okay. Questions number 1. Cool. Okay, so this one is, let me just check something real quick. I'm seeing how much randomized information is in the problem. At risk of sounding repetitive, this one is just like the other problems we've done, right? So this is going to be the same idea of molarity and milliliters to moles, using the mole ratio from the chemical equation to get the moles of the other thing, and then converting back to a molarity. We ready for it? And then, Ashley, I see your question. We'll get to it in just a moment. So, for my problem, I have a 7.07 milliliter sample of nitric acid, which requires 13.25 milliliters of 0.112 molar sodium hydroxide solution to titrate. And I'm going to write down the complete parts first. I'm gonna skip a bunch of steps. I'm going to show you how I kind of think about it. So when I start to see a problem like this, first thing I recognize is the chemical equation. I recognize monoprotic, monobasic, so it's going to be a 1-to-1 mole ratio, taking sodium nitrate and water. And at that point, I can kind of do the rest in my head in terms of the multiple steps. So I'm going to show you kind of how I put it together. I'm going to do 0.01325 liters times 0.112 moles per liter times 1-to-1 mole ratio, 1-to-1, is equal to 0.00707 times molarity. Right? Because we're at the equivalence point, we're doing this titration, I know that my moles of sodium hydroxide have to be equal to my moles of acid, taking the mole ratio 1-to-1 in this case into account. So then I can just divide, and it's going to be 0.01325 divided by 0.00707 times 0.112. That should be it. Right, so once we practice this stoichiometry and kind of spend more time looking for the patterns and the problems. We get much quicker at these. 0.01325 divided by 0.00707 times 0.112. And so for my values, I get 0.209. I get a higher concentration, which makes sense because the equal moles has a lower volume, which means it must be more concentrated. And I also think that's a valuable step in these problems, is after you solve it and you get a number and you get that box that turns green, is like, you did it right. Slow down. Think like, well, what's the physical sense behind this, right? It's not just getting the points, but it's like, does this answer of 0.2099, does that make sense? Right? So looking at this volume and this concentration, the concentrations, it's about double the concentration, 0.11, 0.1, 0.2, and it's about double the volume, 7 milliliters versus 13 milliliters. That totally makes sense, right? Finding that logical piece in the problems as well is really handy for making sense of what's going on. Let's do some callbacks. Prep 2 number 2. I'm gonna pause for this.